Hi everyone, my name is Yulia Chen. I also go by Yuanlei Chen, and I'm a PhD student at Stanford University in Professor Adam Brandt's group. And today I'd like to talk to you about reconciling methane emission estimates from two aerial hyperspectral imaging surveys in the Permian Basin. And hopefully by the end of this presentation, I can convince you that that we are talking about just one consistent single tail of this one basin instead of two. Okay. Sorry, I'm experiencing some lagging. Okay, before I start, I'd like to thank my co-authors at Stanford University and EDF, and also Carbon Mapper and Insight M, and also the funding sources from the Stanford Natural Gas Initiative, EDF, and the Fuel Project for making this project possible. So over the past few years, there have been quite a lot of studies that looked at the Permian Basin and quantified methane emissions from the oil and gas sources. And the technologies included tower-based sensor networks, OTM-33A airborne surveys, satellites, continuous monitoring, and many others. I'm just showing some examples. It is obviously a very ambitious goal if we want to gather all of these studies and compare and reconcile them, and it is out of the scope of this presentation today. So for today, I just want to focus on two airborne studies, which the first one is done by Griffis et al. In the Permian Basin using two hyperspectral imaging spectrometers that are mounted on two different platforms called GAO and the ARIS-NG. And what they found is that in the Permian Basin, they've done multiple surveys in many basins in the US, but in the Permian Basin in 2019, September to November, they quantified a total of 246 tons per hour of methane from oil and gas polluting sources. And this corresponds to about 2.7% of the total gas production in this area during the survey time. And on the other hand, Insight M, which was previously known as Kairos Aerospace, did another airborne survey, also using a hyperspectral imaging spectrometer in the New Mexico part of the Permian Basin. And the result is that they quantified a directly measured emissions of 153 tons per hour of methane, which corresponds to about 7.4%. Now, if we just take the base values of these two studies, 2.7% and 3.4% are obviously two very different numbers, and their error bars don't even touch with each other. So what is happening here? And if we discuss some doubts onto these airborne studies, and if we want to use these aerial data sets and incorporate them into our mapping inventories in the future, then it is kind of important for us to understand the difference. So let's first talk about how similar are these two studies. These are two studies that are similar in study designs. As you can see, the orange polygons here is the study area of the Insight M survey, which is the New Mexico part of the Permian Basin. And the Griffis et al. Use two platforms, the GAO, which covered a more extensive area of the Permian Basin, including both the Delaware Basin and the Midland Subbasin. The GAO covered this light blue polygon at least once, and ARIS-NG, on the other hand, focused on the smaller inner or center area of the two basins. And ARIS-NG, I think, if I remember the numbers right, surveyed the purple polygons at least 7 times. So it provides better temporal resolution. And we refer to the overlapping areas of these two studies, which is outlined by the black polygon as the full overlapping area. And as you can see, all of these three sensors found quite a lot of emission sources in this full overlapping area. So not only are they similar in their study designs, they are also similar in their ways to quantify basin-wide emissions. And briefly, what these aerial studies do is that they just take the plume and wind data and calibrate the plumes based on control releases. And if, for example, there are multiple observations of a single source, then they would just randomly select one of the observations of the plumes. And also this way, they account for the intermittency from different observations. By summing up these persistence-informed source level emissions, we get total directly measured emissions. And I would like to emphasize that the total directly measured emissions is different from the regional total methane emissions because we don't account for those undetected emissions that are within the partial detection range of these sensors that are below the detection limit and from the sources which may not be covered in the survey but are in the survey area. So in this study, we just want to compare the directly measured emissions and we don't need to worry about the undetected emissions. So what could be misaligned? Let's start with the raw reported numbers from the studies. The InsideM study found 7.4% of production loss, and the customer sales study found 2.7%. We did a t-test to compare these two values, and we found a p-value which is really significant, suggesting that the two values are quite statistically significantly different. And we look at different aspects for misalignment. We look at maybe the sensor performance is different, maybe the survey designs are different, or maybe there are different ways of handling processing data. And for each of these aspects, we align them using one of these two ways of reconciliation, namely the design harmonization or a post-facto adjustment. And for you to better understand what we mean by these two approaches, we informally regard the design harmonization approach as the selecting approach, meaning that we just select the most comparable subset of the studies so that the designs are harmonized and we are comparing the most comparable parts. As an example, okay, so if I put two dots in different colors here, that means that this aspect can be aligned with either the design harmonization approach or the post-facto adjustment approach. And the black crosses here marks the approach that we select for this study. And for spatial coverage, we are using design harmonization, meaning that we are only looking at the overlapping areas, and we would just disregard the data points which are outside of the overlapping spatial coverage. And on the other hand, the post-facto adjustment, we also refer to that as the correcting approach. If we apply the post-facto adjustment, then we don't throw away any data, but rather we apply some corrections to make sure that the underlying assumptions are aligned. So for example, the time period, we are using the post-facto adjustment. So even though these two surveys are done in slightly different survey times, we make sure that they are corrected so that they reflect the same production levels for gas in this area. Okay, let's get started with the stepwise alignment, starting with the raw reported values. And the first step that we could think of is to, let's just look at the overlapping area outlined by this black polygon. So once we limit our data to this black polygon, we see that our p-values goes up pretty significantly, but the difference is still there. And we also break things down by the sensors. We are not showing an ARIS-NG purple bar here, but just a GAO bar here. That's because the ARIS-NG primarily just cover this core region. And then we don't think we can produce a number from ARIS-NG that represents the whole overlapping region. So if we further limit the spatial scope of comparison to this inner core production area, which is in this dashed line here, then we see our p-values goes up further. And most of the increased p-values comes from the fact that all of these bars come down, most significantly from Kairos and also very obviously from Cuthbert et al. And by the way, this is the only region, this small region is the only region where we can present you 4 bars, which are from 3 different sensors, and the ARIS-NG bar can, the ARIS-NG can have its individual bar. Now, why do we observe this large decrease in production loss if we limit our spatial scope from the full overlapping area to this core overlapping area? And that's because there are quite significant spatial heterogeneity in the emissions in these areas. So although they're in the same basin, we observe that there's sub-basin level differences in these different areas that's detected by both the InsideM and Cuthbert et al. This is a gridded type of production loss that's shown here, and we see that in the inner or core overlapping area, although this area is believed to have more production, it's more production intensive, but it's less emission intensive compared to the peripheral overlapping area in terms of the production loss. So and the next alignment aspect that we consider is the size limit for direct comparison. Here I'm showing you a graph that shows the methane emission sizes that are on the x-axis, and they're shown in different bins, which are in 1/4 order of magnitude. And on the y-axis, this is the probability of detecting an emission source that falls in a certain bin size per well visit. So these 4 lines here are Insight and GAO, ARIS-NG, and customer data, which combines GAO and ARIS-NG. And in addition to that, I also add 2 studies, which is one OTM33A study done by Robertson et al. That's also in the Permian Basin, which visited 67 well sites. And there's another study that's done by Heracles Lloyd State, which used which used the data from 3 different satellites, including 2 Chinese satellites and Prisma, and an Italian one. That also cover the Permian Basin. So there are many observations that we can make from this graph. First of all, many of these curves, including the arrow ones and the satellite ones, they are not monotonically decreasing as shown by this. This is just a demonstration of what if we see a power law decline of having more emissions which are smaller size and less emissions of larger sizes. So why do we see this curve going up and then going down? And that's mostly because before we reach the peak of these curves, we are in this so-called partial detection range, meaning that we are not seeing or picking up all of the emissions because of the sensor detection limits. And this is evident in both the aerial sensors and also the satellite sensor. And the other observation that we can make is that we see that different sensors see different things. So if we don't have small enough detection limits, then we will miss the smaller ones that are in this region, which are picked up by the OTM33A study. But if we only have 67 well site visits, then it's very likely that we miss these large guys with the probability of detection that's less than 1 emission source that can be detected per 10,000 or 100,000 well visits. So when we want to compare the results from these studies, we need to pick a certain sort of threshold and above which we are comparing while comparing their total emission estimates. So if we zoom into the aerial surveys, which are so the bins here are this time decreased from 1/4 of magnitude to 1/10 of magnitude, and we see that Kairos Aerospace, Insight M, which is now branded as, has a smaller detection limit, or it reaches peak quicker than the GAO and ARIS-NG. And that's because, well, one of the reasons for that is because Kairos has a lower flight altitude than ARIS-NG and GAO. And although ARIS-NG and GAO have almost the identical sensor mounted on these 2 platforms, in the Permian study, the GAO was flown at about 5 kilometers above sea level, and the ARIS-NG was flown at 8 kilometers above sea level, which results in this difference in their detection threshold. So we conservatively pick 500 kilogram per hour, which is one size bin that's next to the peak of the largest peak that we saw from ARIS-NG and the upper end. And we think it's safe to select 500 kilogram per hour because we think all of the sensors would be able to pick up all of the emissions that are above this detection threshold. And this is the result after imposing a size limit for direct comparison. Although 500 kilogram per hour seems to be a very large number, and there should be quite a few emissions that are above this range, we still see it's still a quite significant proportion of the total emissions which are above 0 kilogram per hour. And importantly, this is one takeaway message that I want to show, is that just by imposing a spatial alignment and a size limit for direct comparison, we see that these 2 design harmonizations, they can reconcile the airborne studies, with a p-value now increasing to 0.3, suggesting that there is probably no longer any statistically significant differences between these two estimates. And if we take a closer look, so instead of showing the size limits as 500 kilogram per hour, 500 kilogram per hour as a single data point, now I'm showing a range of detection limits that you can choose from 0 to 1,000 kilogram per hour. And at the right intersection here, you're seeing that how much total emissions, which is reflected on the left y-axis, that are above, that are from sources which are above 1,000 kilogram per hour. So this is the 500 kilogram per hour, which are shown as the bars here. As we can see, the InSight M and the ARIS NG have very similar numbers. And more importantly, they have also very similar slopes going from this range, 500 kilogram per hour to 1,000 kilogram per hour, meaning that the distribution of emissions detected by these two surveys are also quite similar. And interestingly, this slope is also similar for GAO with InSight M and also ARIS NG. What GAO is missing, or why we are seeing a much lower GAO bar than the ARIS NG and the InSight M bar, is because GAO missed some of the large ones that are above 1,000 kilogram per hour. And this makes sense because, as I previously told, the GAO covered the more extensive area at least once, whereas ARIS NG covered the area about 7 times, and InSight M covered the area on average about 4 times. So ARIS NG and InSight M did more surveys in this area than GAO, and therefore finding us the larger ones, which are less likely to be found. There are some other aspects that we need to align, including, sorry, I just need 1 more minute. Okay.
Okay, no worries.
Yeah, and intermittency accounting and also post-facto adjustment. In the interest of time, I'm not going to tell you all of these aspects in detail, but the takeaway message is that even if these are the steps which matters less, and after we impose all of these steps, we end up with a p-value that's still much higher than 0.05, which is the significance level that we used. And the last thing that I want to touch on is that we could also align the coverage frequency, and there's a way that we simulate the variance based on the coverage frequency, and this could be okay, but in the interest of time, let's jump to the conclusions. So if there's one thing that I learned from this detection work or detective work, is that we need to exercise caution for accurate inference. It's very tempting to take the face values from the two studies, 2.7 and 7.4, and claim that the airborne studies give us two different stories of the same basin. But still, as I show, I hope that you also is convinced that there are reasons to believe that there's one single tale of the Permian Basin that's told by the two aerial surveys. And we see that spatial alignment and imposing a size limit for direct comparison are the two most important steps for reconciliation. And for us to do this reconciliation, we don't just need the survey data, meaning just the plumes that reported by these surveys. We also need the metadata, including the survey coverage, imaging time, strength detection limit. And we think these data are very important for us to accurately infer from these studies. And we urge publishers of these data sets in the future could also make these metadata available. We also observe sub-basin level heterogeneity, and that's quite significant. And in this study, we found larger emission intensity observed in peripheral area than in the core production area, meaning that in the future survey designs of aerial studies, we probably can't just focus on the core production area and then draw inference about the entire basin. And we also saw larger spatial variation than temporal variation in the emissions observed. And lastly, coverage frequency matters. As we saw in the example of the GAO, although we think that comprehensive surveys are important for us to do regional quantification, the GAO example shows that maybe sometimes even one comprehensive survey may not be enough for basins with extremely heavy tailed, extremely emission distributions. So if you're interested in this work, I put out a link to this preprint here. And if you have any questions, you can also, I'm going to address that in the question section, and please feel free to email me. Thank you.
Thanks so much for having me. My name is Zichong Chen. I'm working at Harvard, working with Daniel Jacob, the same group with Jack. So today I want to talk about my recent work to develop a global level high resolution monthly inventory of methane emission from rice paddies. So before science, speaking of rice, there are a lot of rice food. The Japanese sushi, Korean rice cake, Chinese rice tofu, and Vietnam rice noodle. So yeah, okay, that's a fun part. And so moving back to the science part, like why do I want to develop a new rice methane inventory? Because for the current inventories, there are high uncertainties. Like global-wise, the Global Carbon Project reports are a range of 25 to 40. For China, it's the biggest rice producer. It gives a range of 5 to 15 kilograms per year. It's quite a big range. And if you look at the middle panel here, it's a special map from EDGAR. It's a widely used emission inventory for methane, CO2, and other air pollutants. And I probably do not need to be a rice expert or like a methane expert or an expert in anything. I can probably tell this figure is probably wrong. And the reason is if you look at Korea, Japan, or the Southeast East countries, it seems like the EDGAR thinks like we grow rice everywhere in the country. That seems unlikely. And if you move to the most right panel, which shows the emission peak month, which is the months that the rice emissions reaches the peak. And yeah, it's pretty obviously like for the entire China, EDGAR assumes all the rice emission always reach at June. And for India, it's always like August. So say if I'm a farmer, I grow rice, like this is the border between China and the country here. So it's almost impossible for the rice to know, okay, I'm from different countries, I should pick at a different time of year. So as you can tell, special pattern, the temporal pattern, also the magnitude with the high uncertainties. So I want to build a new one. For this high uncertainty, it's very difficult to use them. Set the baseline for the rice emission control strategies. So say if I want to build a new inventory, I want it to be really high resolution, very accurate description of the temporal spatial patterns. How should I able to do that? If I look at the IPCC inventory-based method, emissions simply equals the rice area times emission factor. It's not that difficult, right? So we can just do it. So I want to take one step back to first think about how rice paddies even produce and emit methane at all. The figure here shows, first of all, and the rice paddy needs to be flooded. When it's being flooded, it cuts off the oxygen supply to soil and creates an anaerobic environment, right? Then the soil organic matter is decomposed in this anaerobic environment. Then it produces methane as a very important byproduct. So the next question to ask ourselves is like, how is it even escaped from the soil and to atmosphere? So there are many three pathways. There are diffusion, that's a very small part. And also sometimes you walk by a lake, a river, you see some bubbling, then that's another pathway for methane to bubbling out. But the takeaway is the plant transport is actually the major pathway, account for more than 90% of these emissions. So that's a spongy tissue called parenchyma. It's like a spongy tissue that connects the shoots and the roots. That's how methane is kept away. And another thing is we know the rice grows during the season. And then when the rice grows bigger and bigger, so that means two things. That means there are more escape from the plants. And meanwhile, that means there are more soil organic matter to be decomposed to give you more methane production. So the takeaway for this slide, the two things. So the plant, rice plant is a major takeaway. And also the rice plant growth, the phenology matters. So then we do a little bit summarize. If we want to estimate the rice paddy extent, what information should we know at least? first, very important, we need to know if this is a rice paddy, right? And then we want to know if this area is even flooded. And we also need to know what is the inundated vegetation extent, as we just talked in the last slide. So one sentence summary is we need to know the seasonal rice paddy map with the accurate inundated vegetation extent at a really high resolution. So how should we able to do that? Then we have satellite data. The NASA satellite data is launched by NASA, but being operated by different institutions, can map the open water and inundated vegetation at a 30-meter resolution. Here the figure shows you different generations of Landsat. Now we are currently at the Landsat 9, and there will be Landsat next will be launched in 2030. It has been in service to image the Earth since 1972, more than 50 years. And there has a 16-day revisit time with 30-meter pixels, observed at a visible near-infrared and shorter wave infrared bands. So with all that information, we are able to observe the open water inundated vegetation. The right figure very briefly I want to show how we are able to do that. And first of all, what do we get? We only have the Landsat image from Google Earth Engine, by the way. And then it's very similar to our multiple linear fit. And we are able to use a spectral mixing method to get what information do we need? We need to know the fraction of water, the fraction of vegetation, the fraction of soil, right? And then we can get something like this. And then we bring in further information. For example, the elevation. We know the rice is always growing in a low-lying elevation, and also think of the slope. If the slope is too steep, then the water runs away. So we don't want it to be that way. And anyway, we tune the model very extensively for the rice mapping, and so we are able to get the very good rice map at a monthly scale. So if we revisit this calculation here, the rice area part, inundation seasonality is being taken care of well. So we move to the emission factor side. So first of all, speaking of emission factor, we think of IPCC, right? IPCC recommend use some values to use. And the figure here shows, actually, the purple color shows the entire Southeast Asian countries. There are many countries in it. The IPCC suggests only one value for all these countries, the 1.22 kilogram per hectare per day for it. We know that probably means bias, because based on measurement, that shows the very right part of the table. For different countries in this purple area, from the Philippines to Vietnam, the emission factor actually range pretty large, from roughly 1 to almost 3.6 from different countries. So if we go with this very coarse IPCC value, that means high uncertainty for us. So instead, we use this measurement-based country-specific emission factor. So if you look at the calculation again, rice area, emission factor, all taken care of. So now I'm ready to show you some delivery results. And the right figure shows we graded the data to like a 1 kilometer resolution. That's good enough for us to use, for inverse modelers. And at a monthly scale for year 2022. And I'll start from the left part. Let's summarize growing in California and also Louisiana, Arkansas, Texas. That's for the North America. And also summarize growing in Brazil and also Sahara or Africa. That's my previous work working on this area. And most importantly, that's area, the east area, south area, southeast area. We see tons of rice being grown. That all makes sense. What's more important is we are able to deliver its resolved seasonality. Previous inventories, like Edgar, the seasonality as I just showed at the very beginning, is very poorly described seasonality. Or some inventories just do not have that information. But this information is very important to us to understand the mechanism of the emissions or better guide us for climate actions. And as you can tell from the south to north, as the temperature being warming up, you see the rice emission being popping up from the south and then gradually move to the north part of northeastern part of China. And the right part gives you America. You see the rice being popping up from Texas and slowly and gradually to move north to Louisiana and Arkansas. That all makes sense. So in the next two slides, I want to very briefly break down to some very interesting countries and to show the how our method and our inventory being a good one. So the first one I want to show is India. You can see rice being growing in, almost everywhere in India, especially in the right part of the country. And so very interesting, it shows the seasonality here. And we see high emissions, only see high emissions during July to October. We wonder why. The reason is for the rice cultivation, it's actually the agriculture or cultivation in India is heavily relied on rice. So for the June to October, it's India's summer monsoon season. 80% of the annual rainfall falls on this time of period. So it makes sense, right? The farmers want to grow their rice during when there's enough rainfall to use for their irrigation purpose. And then, so it makes sense that when the rice being grown in June or July, we see emissions popping up from rice. And at the time of end of October, November, there is harvest, and then there also rice emission also goes down. So that's India. Then we move to it's a neighboring country, it's Bangladesh. Bangladesh is a small country surrounded by India. As you can show the map here, it's the rice is being growing in a really big coverage of the country, and that's aligned with the country's policy to grow more and more rice. And so it's very a neighboring country of India, and it's experiencing the very similar like the monsoon season climate. But if we look at the seasonality, it's quite different. The different part is like we almost see high emissions almost all year around. So the reason is, first of all, for the country, rice is harvested 3 times a year. It's a triple cropping system. It's based on the local climate, also the management. And also, even though it's a very small country, it's the third largest rice producer, only after China and India. So it makes sense the rice is being growing all the time, and so you see the high emissions all along. So if we compare to the two neighboring countries, and the beautiful part of our work, I think, it's like we don't need to do like some survey work to know Bangladesh is harvested 3 times a year. We don't need to know in the summer monsoon season it's during from the June to October. The satellite can do that for us. Also, same thing for other countries. So that's a beautiful part of our work. We are able to capture the impact of local climate and management practice to effect on the rice methane emissions. So, and the last slide of my work is that you might wonder, rice is a food we rely on for living. And if we want to reduce rice emissions, we of course want to also guarantee the food security, right? So there are a couple of methods I can show you here to do that. The first one is the local high yield cultivar, and with it doesn't need that much water, so it gives you lower methane emissions. And also there's a non-continuous flooding practice. The idea is that in the middle of the rice season, for some time, we take the water out to save water, and meanwhile, there's a lower methane emissions. The second one is to remove the straw and lower manure addition. So there are lower soil organic matter to be decomposed to produce methane. The last one is my favorite. It's putting ducks into the rice paddies. So ducks are pretty naughty as they're being moving around all the time. So it's going to disturb the water and increase the dissolved oxygen concentration. So there are less methane being produced from the rice paddies. So our work is that we can help you locate the area and timing for the mitigation priority. Basically, you can help you to know where is the best location to put this cute naughty ducks. And one sentence is for the take-home message is that this method can be applied not only to the rice paddies, can also be used for natural wetlands and lakes. Thank you. That's all I have.
Hello, everyone. I'm Qining, and for today's lightning talk, I'm going to give an overview of Project Astra. So the Project Astra is a multi-phase project aiming at advancing methane detection and reduction technologies using the continuous monitoring systems, specifically at the oil and gas production fields. And our final objective is to transform the methane emission detections from those labor-intensive surveys to sensor-intensive continuous monitoring. And those are expected to provide quick detection of emissions at high spatial and temporal resolution, as well as at low cost. So Project Astra is led by a research team at Center for Energy and Environmental Resources at UT Austin. And the team involves a large group of people, including both grad students and research scientists with expertise in like field operation, atmospheric modeling, data analytics, and automation, etc. And we also have multiple industrial partners. So I'm part of the Astra team, and I'm responsible for network designs and data analytics. So I'm happy to take any questions relevant to that. We also have a news page and a technical site. So if you want to stay tuned for our latest research updates, please visit our websites. So the Project Astra started in the year 2020. And by the end of 2023, we have completed the phase 1. Phase 1 has 3 subparts: the methane sensor intent comparison, the digital methane challenge, and running the Project Astra pilot. The methane sensor intent comparison is a 9-month in-field testing and selection of sensors used for the Astra pilot region, and it was done in the Midland County in the Permian Basin. And in the digital methane challenge, we developed a digital twin of the pilot area, and we performed dispersion modeling to generate synthetic emission dataset to try to determine the optimized design of sensor mesh network and the data analytics required to identify emissions. And then with these pre-testing and understandings, we started to run the Project Astra pilot since February 2022 in the Permian Basin with real-time methane concentration data measured by a network of around 60 sensors deployed at about 50 oil and gas production sites at second and minute resolution. And then also at some selected sites, we have measurements of ethane concentrations and meteorology condition measurements as well. So I'm going to briefly go through these projects and our main findings one by one, but not really in deep. It's more like an overview. So the first was the methane sensor intent comparison. We performed a 9-month testing from October 2020 to June 2021 with 7 commercially available low-cost methane sensors deployed, tested, and intercompared. We tried to answer questions during this in-field testing. The first was what precision and accuracy can be provided by those commercially available low-cost methane sensors. And we found that at second resolution, multiple sensors can have 10 ppb sensitivity, and at a 1-minute resolution, multiple sensors are able to detect 500 ppb concentration changes. And the second question we tried to answer was what's the data capture rate, and also how's the sensor performance consistency. We found that multiple sensors, both high precision and medium precision sensors, had pretty high data capture rates, on average over 80%. And the sensor performance were quite consistent as long as there are no severe weather conditions. So that provides us the visibility of applying those low-cost commercially available sensors in the field. So this is a picture of where we apply those sensor intent comparison study in the Permian Basin. This work was published in a preprint in 2022, and the lead author of this paper was Dr. Vince Torres. He was our field expert of the Astra research team. And then the second part of Astra phase 1 was the digital methane challenge, in which we developed a digital twin of the pilot area. We performed dispersion modeling to generate synthetic emission dataset to determine the optimized design of sensor mesh network. So although the continuous monitoring systems are operated continuously, still not all emissions can be detected because of the shifts in wind conditions and meteorology conditions. As what you can see here, this is an example time series detection and non-detection bands by a group of 4 sensors on an ideal LAAS site. So there are some detections, but still there are some blank periods where we got no detection at all, although the emissions are continuously happening. So the detection efficiency depends on like source characteristics, the meteorology conditions, the sensor detection limits, and sensor placement strategies, like how you place the sensors. So we performed this study to determine an optimized design of the network and also evaluate the efficiency of such continuous monitoring networks. The first key question we tried to answer from this work was how many sensors are needed and what sensor precision is required. And from our study, we found generally 1 to 4 sensors per site could provide rapid detection of emission events compared to those periodic screening. And specifically, if we place 1 sensor per site, it's still capable of detecting large emission events in a short average time to detection within 1 day based on the conditions in the Permian Basin. And surprisingly, the time to detection and like the detection coverage and other performance characteristics are not very sensitive to the sensor detection thresholds or the sensor precisions, but more sensitive to how many sensors you place on the site and how you place those sensors on the site. So we had 2 publications relevant to this work. So feel free to read those, and if you have any questions, reach out to me. And then the second key question we tried to answer during the digital methane challenge was, can equivalency with leak detection and repair be established? So in this work, we developed a hypothetical model site based in the Permian Basin with a pad of 2 wellheads surrounded by 12 potential sensor locations. And we had a group of 100 sites like this just to simulate regional behavior. And then we put in small leaks and large emission events on top of that. Our analysis showed that the deployment of 1 continuous sensor per site with the rapid response to only the single largest emission event occurring across the 100 sites would allow the screening frequency to be cut in half, while preserving the same amount of emission reductions. And this was also published in a preprint in 2023, and the lead author of this work was Dr. Colette Schissel, also part of the Project Astra research team. Then the last question we tried to answer during the digital methane challenge was how to define the detection limits. And these are especially important when for example, the regulatory agencies and operators need to develop performance metrics for these continuous monitoring systems. And usually these performance metrics are expressed in emission rate units. However, what the continuous monitoring systems detect are concentration enhancements rather than the emission rates. So we'll need to translate from concentration detection matrix to emission rates or detection limit matrix. The detection limits for continuous monitoring systems will depend on meteorology conditions, characteristics of the emission sources, the positioning of the continuous monitoring system devices, and also the amount of time allowed for the system to detect the emission source. This means that when certify the performance of a continuous monitoring system, it will require test protocols with well-defined emission rates and durations. So in this work, we kind of provide a framework for defining the detection limits for continuous monitoring systems based on our synthetic data set. And this was recently published in Atmosphere. So yeah, here's the publication link. And finally, let's move to the third part of Astra phase 1, which was the Project Astra pilot. We started to run the Project Astra pilot since February 2022 in the Permian Basin, and this work is still ongoing, in which we have a network of 60 sensors, including both high-res and low-res sensors from 3 different sensor manufacturers. And those sensors were deployed at around 50 oil and gas production sites with at least 1 sensor per site. Those 50 oil and gas production sites were from 3 different operators. So we work with those operators for event detections. The emissions were measured continuously at minute or second resolution, depending on the ability of different sensor manufacturers. And the emission events are being reported to operators and throughout the pilot region. So the key question we're trying to answer during this Project Astra pilot are how to correct for background concentrations and recognize true positive detections, and how to define an emission detection. For example, here you can see very different from the synthetic data set. When it comes to the real world, we get a lot of background fluctuations, and some rapid background methane changes are false positive detections. So how can we filter the true signals from that? And also the other question we tried to answer was how to determine the emission event durations. And because of the data confidentiality, we're not yet ready to release the analysis and results from these studies, but we're planning to publish our findings as soon as we can. So yeah, I think this concludes most of our work during the Project Astra phase 1. And then last October, we got funding from DOE, and that marked the start of phase 2 of Project Astra. In phase 2, we'll expand sensor networks from current production sites to gathering, boosting, and processing sites, so those midstream sites. And this part of work is currently ongoing. We'll also continue to work on emission detection algorithm and automation with a focus on being able to characterize the frequency and duration of emission events and to quantify the emissions. And hopefully this will support the local emission inventory improvements. So if you're interested in our work, you're welcome to follow our websites and stay tuned for our latest research updates. Thank you.